In the first part of this section, we talked about what a function is, and we talked about its domain and range. In this part of the section, I'm going to talk about various ways to construct various functions, and different ways to combine functions that we already have. First thing I want to talk about is what's called a piecewise function. Basically, some functions are not given by the same formula everywhere. We don't really want to say that a function is a formula because we want to be able to have a little more flexibility. A particular example of this might be the absolute value. The absolute value of x is actually given by two different formulas depending on what the value of x actually is. If x is a non-negative number, if it's 0 or positive, then we're just going to leave x alone. We just say the absolute value of x is equal to x in that case. If x is a negative number, we want the absolute value of x to be the positive version of that number. In other words, we're going to introduce a negative to change the negative of x to a positive. So this has one formula for non-negative x's and a whole different formula for negative x's. That's why we call it piecewise. There's two pieces to this function. And we use this fancy brace thing here to basically say to include all the pieces together. Let's look at an example of this. Let's look at problem 22. Here we have f of x is equal to two pieces. The first piece, when x is less than 0, we have 3x plus 2. When x is greater than or equal to 0, we have that f of x is 2 minus x. So if I were to say put negative 1 into here, so f of negative 1, I would have to look and see which one of these is satisfied. In this case, because negative 1 is less than 0, I would use this formula here. I'd use the 3x plus 2. I would put negative 1 for x. We have a negative 3 plus 2, which gives me a negative 1. If I were to plug it into the wrong formula, I have 2 minus negative 1, which would be a 3. I want to make sure I use the correct one here. Now, graphing something like that is a little tricky. If we want to graph a piecewise function in Geogebra, we're going to have to use an if command. If you've done any programming, this should be somewhat familiar to you. But here I'm saying that f of x is going to equal, when x is less than 0, I'll put my condition here is that x is less than 0. When that is true, I want it to graph 3x plus 2. When that's not true, I just put a comma here and I put 2 minus x. And that actually will fill in. It'll say x is less than 0, and it'll say it puts otherwise here. That's when x is greater than or equal to 0. But that's a graph of what that particular function would look like. Now, I'm not going to do too much with piecewise functions here, so this is not necessarily super important for you to know how to do this, but just be aware that we have a lot wider variety of functions than just formulas or equations. This is as valid of a function as any other function, like a quadratic or a fraction or anything like that. This is just as valid as those. And we don't even have to just have two pieces like we have here. Both of these had two pieces and they're both changed at 0. That neither one of those is necessarily has to be true. We could have something like f of x is, let's say it's 5 when x is bigger than 2. It's 2 when x is less than negative 2. And if x is between, let's say negative 1 and 1, it's equal to x squared. This is maybe not the most useful function, but we can graph it and we can talk about it. And our function looks something like this. It's 2 from negative infinity to negative 2. Between negative 1 and 1, it's just the quadratic x squared. And then from 2 to infinity, it has a y value of 5. And note here, this is not defined for negative 3 halves. Or you could say negative 1 1/2. There is no value there. That's not part of the domain. So here, this is an easy way of getting the function that doesn't have pieces that are in the domain. There's a whole negative 2 to negative 1 and 1 to 2. Those two intervals are not part of the domain of this function. The range here would be, well, it'd be from 0 to 1, but then it'd also include 2 and it'd also include 5, but it wouldn't include anything else. So there's a lot of different possibilities with functions. And if you are interested here, the actual way I graphed this thing was I used that same if command, but I had to nest like I guess 4 of them together. It's kind of a little awkward to do this. I'll admit that, but it's possible. But the point here is just, again, a function is not an equation, even though most functions that we're going to be working with are given by equations. They're just a little bit broader than that. All right, let's switch gears a little bit. Let's say we have some functions, and we want to build new functions out of those functions. In fact, this is going to be a very useful thing for us throughout this course, because a lot of the rules that we'll have for calculus will depend on knowing some basic rules for some basic building blocks, so things like powers of x, exponentials, logarithms, all that kind of stuff. And then we have basic rules for these, and then we know how to put these together to make more complicated functions. And there will be rules for how to deal with those combinations. So let's say we have two functions. We have f of x, and we have g of x. Technically here the functions are f and g. Though a lot of times we'll just write them as using the of x notation. What are some possible ways to combine these? Well, we just have our normal arithmetic operations. We could add them together, we could subtract them, we could multiply them, we could divide them, and all those will give, actually let me go ahead and put the names here. All these will result in brand new functions. If I add them together, I'll get a new function. If I subtract them, this is also a new function. If I multiply them, new function as well. I mean, there's some, obviously if one of these functions was equal to 0 to begin with, this would not be a new function, but a possible new function. And we could also divide them. And we get a new function. Of course, here we also had to worry about if g is 0, if we get 0 values on the bottom, we had to make sure we exclude that wherever that happens from our domain. Things like that. Let's look at a problem where we do stuff like this. Let's look at problem 36. In problem 36, they give us the function f of x is equal to x squared plus 5. Function g of x is equal to the square root of 1 minus x. We want to combine these in various ways. There's actually 6 different parts to this problem. The first one is asking what is f of x plus g of x. Now this isn't a super complicated question. We're really just taking these two formulas for f and g and we're adding them together. I'll take my formula for f, x squared plus 5, and my formula for g, and I'll add that onto the end of this. Part B asks us to do basically the same thing, except we are subtracting g. So I'll have my f is x squared plus 5, and this time I'm subtracting the square root of 1 minus x. Now, one thing here that they didn't ask for, but I want to make clear, if we were to ask for the other way around, g of x minus f of x, we would put our formula for g of x first. And when we subtract f, we need to make sure that we realize that there's two terms there. We're subtracting that entire sum, which also means we will have to distribute the negative if we don't want to put the parentheses. So we have the square root of 1 minus x squared minus 5. Part C, they want us to multiply these. What is the product? Well, we just take this thing. Remember, we kind of do need to put it in parentheses like we have here, because this entire x squared plus 5 is going to be multiplied to the square root. So the quantity x squared plus 5 multiplied by the square root of 1 minus x. Don't write this as x squared plus 5 times the square root. That's not the same thing. So be very careful. If you're in doubt, go ahead and include parentheses. Finally, we're going to go ahead and divide them. That's part D. So we take our formula for f, and we put on the bottom the formula for g, and we're good. Now, one thing we can note here is stuff about the domain. The domain of f is all real numbers, whereas the domain of g, here, keep in mind we do need to not have a negative under the square root, so we need that x is greater than or equal to 1. The fact that the domain of g is not all real numbers will have an effect on the domains of these combinations. For instance, for the sum, the difference, and for the product, all these turn out to have the exact same domain as g did. All these will have domain x is greater than or equal to 1. Or, sorry, x is less than or equal to 1. We need, because we're doing 1 minus x, we need the x to be smaller than 1, or else we'll get a negative. So A, B, and C all have the same domain as G does. If the domain of f was not all real numbers, if it excluded some, we'd also have to exclude those from A, B, and C. With division, we actually have the additional condition that we can't have 0 on the bottom. That's kind of comes out of nowhere, just because of the fact that we have a division as our operation here. So we also need to not have the square root of 1 minus x be equal to 0. That means we have to exclude 1. So the domain here for g and for a, b, and c is from negative infinity to 1, including 1. But for d, we now have to exclude 1, just because we can't divide by 0. Now, it is also frequently useful to give names to these new functions. So here, for addition, I might do something like f plus g of x. Basically, I'm defining a new function that I'm going to name f plus g. That is a new name. That's not a formula. It doesn't have any definition other than the one we're just writing right here. That's just the name of the new function. Similarly, for subtraction, I'll write it as f minus g. For multiplication, I'd write it as f times g. And for division, I would write it as f divided by g. These are just new names for new functions that are given by these formulas. But of course, the notation that we're using here is trying to make it clear what functions we're defining. So we don't really have to do much guessing. A lot of times I'll just go ahead and write them out in like f of x plus g of x instead of f plus g of x. But sometimes this notation can be quite useful. There's one more way to combine functions that is actually a lot more interesting than what we had in those last few slides. It's called composition. Basically, here we allow the output of one function to become the input to another function. If we think of a function as kind of a machine that takes a variable in and eventually spits out another variable, we could say we take that new variable and plug it into the machine of another function and output a third variable. Let's say z, just to follow the pattern of x, y, z. So this new function would basically go from x to z, where we kind of just ignore the fact that we went through y. So maybe we have some big machine inside there's two smaller machines where it takes in the input, and in the middle where we don't actually see it, it gives us y, and then eventually gives us a z that comes out of the whole big machine. We write this as f circle g. That's our notation for what we'd call this. But most of the time we'll write that instead as f of g of x. Actually, need to be careful here. What goes inside first? I put f in first, so I'm going to need to swap the order here. So this is f. F goes first, so f needs to be here. Then g. G takes in the takes the output of f and puts it through g. And we want to keep this order, this g followed by f. So f circle, or g circle f is what we want to put there. Writing it in this notation makes it a lot easier to keep track of which order we're supposed to have. Let's look at an example of doing this, though. Let's look at problem 36. Here they give us the function f(x) equals x squared plus 5. Now note this is the same problem that we were working on a moment ago. We just didn't do part e or f yet. And we had the function g of x is equal to the square root of 1 minus x. Part e asks us to do f of g of x. They actually are not even using the circle notation here. I'm probably just not going to be using the circle notation most of the time. So we'll just keep in mind that our composition is when we put one function inside of another function. We want to know what is this composition. What happens if we put g of x inside of f of x? Note that just means that we are putting in the formula for g into the function f. And that means that any x's that we have in our formula for f, we need to replace those with a square root of 1 minus x. This x here needs to be replaced by a square root of 1 minus x, but everything else stays the same. Now we can actually simplify this a little bit. The square root here can cancel with the square and leave us with a 1 minus x. And in fact, we can then combine the 1 and the 5 to get a 6 minus x. Part f, they ask us to do the other direction. What happens if we, instead of putting g into f, we put f into g? This is a similar process. We're taking g, but instead of putting x into g, we're putting the formula for f. We're putting the x squared plus 5 into g. And that means anywhere there's an x in our formula for g, we now need to replace it with an x squared plus 5. But also keep in mind, we're replacing that entire x, so this negative that's being applied to that x has to apply to the entire x squared plus 5. We can go ahead and distribute that negative if we want to. So we have the square root of 1 minus x squared minus 5. And then we can combine the 1 and the 5 to get a negative 4. We have a square root of negative 4 minus x squared. Now there are a few things to note here. First of all, note that we got a completely different answer depending on the order that we did. Composition is kind of like subtraction and division, where the order does matter. It's not like addition or multiplication. If we switch the order of our composition, we can get a completely different answer. Now, there are a couple cases where we do get the same answer, but those are very special cases. So just assume that we're going to get a different answer anytime we switch the order. The other part is, what about the domain of these functions? In our first example, f of g of x, note that the domain of g, we said the domain here requires x to be less than or equal to 1, or else we'd have a negative under the square root. This actually technically holds for our composition, even though when we simplified it, we only got 6 minus x, and 6 minus x is a formula that works for any value of x. But technically, when we're dealing with the composition, we have to insist that x has to be less than or equal to 1. I know that might feel a little weird that we're insisting on that smaller domain, but there are some situations where if we do not realize that our domain the composition itself and not the formula is smaller than what we expect it to be. If we don't realize that, sometimes we can lead into some issues where we try to use the bigger domain and for that composition, and we come to some contradiction. But most of the time, we're not going to have to worry too much about that. Most of the time, in a lot of what we're going to be doing in this course, we're going to be looking at something that we have out here and then trying to interpret it as a composition in order to work with it. And not usually will we do something like take 6 minus x and then introduce a square root where we didn't have one to begin with. So most of the time, we're not going to be dealing with things that simplify like that. On the other hand, we do have a bigger problem in the second example. When we look at g of f of x, notice that whatever value of x that we plug into here, x squared is a positive, x squared is non-negative. It could be 0. But negative 4 minus x squared is always a negative number, because we're always taking negative 4 and we're subtracting something that's bigger than 0. We're always going to be, at the biggest, we'd be at negative 4. And yet we have this negative number under the square root. That's kind of a big problem. So really what happened here is that the range of f, the range of x squared plus 5, is numbers that are bigger than or equal to 5. But the domain of g is numbers that are less than or equal to 1. Since there are no numbers that are bigger than 5 and less than 1, then no matter what value of x that we choose, this whole thing breaks. So in this particular example, in part F, the composition order results in no function at all, which is a possibility. We don't always necessarily get a function if we have these problems with their domain and range. But we also sometimes can't really predict that if we have some trouble finding the range of one of our functions. So, just something to watch out for. Let's do one last example, and then we'll go ahead and end this video. I'm going to work on problem 40. So in this particular case, we have two functions. We have f of x is equal to 1 over x. We have g of x is equal to x squared minus 1. And they ask us to find 6 different answers. Part A, they want us to find f of g of 2. So they're literally just trying to have us find one particular answer. Now we could go ahead and find the general formula for the composition if we wanted to. We'll actually eventually do that. But here we can do it piece by piece. Since we know we're plugging in 2, so we see what happens to 2 if we plug it into our functions. We plug 2 into the function g. We have 2 squared minus 1. That means we have 4 minus 1. So we get a 3. If we then take this 3 and plug it into f, basically put 3 into the formula for f, we get 1 over 3, or 1/3. And that's the answer that we want overall. The composition is what happens when we follow both of the arrows. Part B is going to ask us a very similar question, except the other order. We're still plugging in 2, but now we're putting it into f before we put it into g. So we take 2, we plug it into our formula for f, we get 1 over 2, we get 1/2. If we then take 1/2 and we plug it into g, well, we have 1/2 squared minus 1, or that's 1/4 minus 1, or -3/4. So -3/4 is our answer. Part C, similar to part A, we have f of g of -3 this time. So we're taking -3. We're first going to put it into g, because that's the first one the -3 sees. We put that in here. We'll go ahead and write it out this time. -3 squared minus 1. -3 squared is a 9. Note that it's not -9. That negative is being squared as well. So -3 times -3 is a positive 9. 9 minus 1 is 8. We're going to take that 8. We're going to plug it into f, because f is the next thing that we see. Well, f just takes it 1 over what we put into it, so 1 over 8. And so 1/8 is our answer. Kind of need a little bit more room for the other parts. So part D, this time we are putting it g followed by f. And the inside here is actually a 1 over the square root of 2. So kind of got a nice, interesting number in there. We're going to take that number. The first thing it sees is f. We're going to plug it into f first. Remember what f does. It takes 1 over that. Well, that's basically taking the reciprocal. If it's already 1 over something, when we take the reciprocal, we just flip it upside down. So 1 over square root of 2 becomes the square root of 2 when we plug into f. We're going to take that square root of 2 and we're going to plug it into g. So we just follow this formula. We take that square root of 2, we square it, and we subtract 1. Of course, square root of 2 squared is 2. When we subtract 1 from 2, we get 1. Moving on to part E. So here they're kind of giving up on putting numbers in. We're going to go ahead and just find formulas. What happens to any x that we plug in? And this is similar to what we were doing on problem 36 before. We're taking f and we're replacing the x that's in f with the formula for g. The formula for g is x squared minus 1. So I'm putting x squared minus 1 into f. That means any place I see an x in my formula for f, I'm going to replace it with an x squared minus 1. So I have a 1 over, instead of x, I have x squared minus 1. And that is my formula for that composition. If I look at the other order, g of f of x, so I have my formula for g, but in that formula for g, I need to put in my formula for f. So 1 over x is what I have for f. Oops. I'm going to take my formula for g, and anywhere there's an x, I'm going to replace it with a 1 over x. That means I have a 1 over x squared minus 1. I'm going to go ahead and take that 1 over x squared and turn that into a 1 over x squared. Kind of read that the same way, but basically when you have a square of a fraction, remember you can square the top and the bottom. But 1 squared is just 1, so it's 1 over x squared. Also note here that these are different functions. So don't try to say 1 is 1 over 1 and then subtract the denominators. We're not allowed to do that. We could subtract numerators if we have the same denominator. We can't do the same thing with subtracting denominators with the same numerators. In fact, these two functions don't even have the same domains. The domain of part f is all numbers except for 0. We can't plug 0 into this function or else everything blows up. For e, we actually have 2 points that we leave out. We can't plug in 1 because 1 squared minus 1 is 0. We also can't plug in negative 1 because negative 1 squared minus 1 is also 0. So this has 2 missing points. This has 1 missing point. But hopefully that gives you an idea how we handle compositions, how we handle plugging formulas into functions, how we replace the values in our formulas, and all that kind of stuff. But I'm going to go ahead and leave that here. In the next section, we'll actually start some stuff that you did not see in college algebra, and we'll actually essentially get into actual calculus when we start talking about limits. So things are about to get more interesting and less review. So I'll see you then in our Wednesday video.